Dear students, welcome to the topic Electrostatics. Here we are starting a new lecture series related to electrostatics. In this video, I will give the details of electrostatics, a brief introduction, the aim behind electrostatics and the topic that we are going to discuss in the coming videos. Okay, let us start with the basics of electrostatics or a summary related to electrostatics.
We know that any electrostatic problem starts with a stationary charge. It is a problem of stationary charge and the associated electrostatic field. The charge usually in electrostatic we represent in two forms, the basic forms. One is a source charge and the other is a test charge. By source charge we mean something that generates an electric field. Usually the source charge is represented by the letter small q. And we can see that this charge produces some electrostatic effect around this point charge, and that region is called the electrostatic field. It is a region around a source where some electrostatic effect is experiencing. And since it is a static problem, we have to assign a coordinate system to the source and the associated field region. You can see that since it is static, it is stationary, its magnitude is constant and also its position is constant. And if we consider the electric field region, that electric field region will always be a static one, there is no change. And if we measure the electric field at some location, its value also will be constant, no change. And the charge placed, which is responsible for the electric field, is taken as the source charge, and usually we represent it in terms of the letter small q. And in order to find the effect produced by the source or to measure the field produced by the source, we will use another charge, and that is represented by the letter capital Q, and it is called a test charge. The magnitude of the test charge Q should be much less than the source charge. That means when the test charge is placed in the static field region, it should not affect the already existing field. The magnitude of the test charge will be negligibly small. And in the limiting case, we assume that it is very small. Usually, sometimes it is represented as dq. And we are identifying the force acting on the test charge. And from that, we are able to find the electrostatic field generated. So, electrostatics is always dealing with the stationary charges and the associated electrostatic fields. So, in other ways, we are able to say this problem like this. It is a cause-effect principle. The cause means the charge in this situation, the stationary charge, and which is responsible for the electrostatic field. And in this case, the effect is the field. The reason for the effect is the cause. So once the exact nature of the cause is known, the effect can be identified. And in the case of any electrostatic problem, we can draw a figure somewhat like this. Stationary charge is the cause, and the electrostatic field is the effect. This cause-effect principle, we can extend this cause-effect principle further into magnetostatics also. In magnetostatics, there is a cause, and that is a static current, and the effect is a magnetic field, that is a static magnetic field. So in that case, it is static current and static magnetic field. We can conclude this in another manner. That is, the aim behind any electrostatic problem is to find the electrostatic effect due to a source, that is the electrostatic field E. To find the electrostatic effect, that is the electric field. Any complicated problem, the final ultimate aim behind that will be find the effect or find the electric field produced by that. And we can see that the source or the cause in the case of electrostatics may be of different form, and that may be in the form of a point charge. It is located at a point like R0, or maybe a collection of point charges, means different point charges here and there distributed or scattered. The electric field is generated by the entire charge points, different Q1, Q2, Q3, etc. Then another charge distributed over a line is usually called as a line charge. Then the possibility is a surface charge, then uniform distribution over a surface, a plane surface, or the general form. It may be in the case of an volume distribution, charge distributed over a volume. So all these type of charge distributions generated electric fields, and the generated electric field has to be evaluated. That is the problem. And in order to tackle this situation, this problem, we have two methods. The first method, that is the most general method, is by making use of Coulomb's law. And Coulomb's law we are familiar as the force between two charges in the form of two charges. That is a charge small q and a charge capital Q. We place these two charges at distance r apart. Then the force between these two charges is taken as F is equal to 1 by 4 pi epsilon 0, some constant, into Q divided by r square. This is the simple expression for the Coulomb's law. And by making use of the Coulomb's law, the force acting based on Coulomb's law, we can define the electric field E as the force per unit test charge. So if we letting the test charge Q to be unit magnitude, that is 1 coulomb, then the force acting will be named as the electric field E. So it is a force. Electric field E is a force. It is the effect due to the cause charge. Okay, so this is the most common and simple method to identify the electric field due to an electrostatic problem. Now, another important problem, that is method, is the use of Gauss flux theorem. In Gauss flux theorem, the statement is quite popular, that is the total normal electric flux over a closed surface is equal to 1 by epsilon 0 times the charge enclosed by the surface. That is, in the charge region, we will consider a closed surface and we will find out the electric flux emerging out through the closed surface, normal component of electric flux over the closed surface, and we'll take the total of that normal component, that is closed surface integral E dot ds, etc. And we can equate that to the total charge within the volume divided by epsilon 0. And we can see that this equation is of very much importance, as sometimes closed surface integral E dot ds is equal to Q by epsilon 0. This is a basic form of Gauss flux theorem. This equation is very much important for certain specific cases having some symmetry. We know that for a point charge, there is a spherical symmetry for the field distribution. Suppose if we consider a distance r away from the point charge, we can see that over the surface with radius r, all the points will have the same electric field, both in magnitude and in the same direction, along the radial direction. So the electric field is constant over the spherical surface. The same thing is applicable for charged sphere, a conducting sphere or a dielectric sphere, etc. If we construct any sphere around that, we can see that the electric field is constant over the sphere. So this is a symmetry situation. In this case, it is very easy to use Gauss flux theorem to find the electric field at a distance r from the source. There are other situations also having symmetry, like a cylindrical symmetry and a plane symmetry. For example, if we consider a line charge, a infinitely long charge, line charge, then there is a cylindrical symmetry. Means if we construct a cylinder, a cylindrical Gaussian surface, means over the curved surface of the cylinder with r as the radius, the electric field will be constant. So it is a problem of cylindrical symmetry. Then if we consider a capacitor, we can have a capacitor, two parallel plates, and we can construct or identify some plane having constant magnitude and direction for the electric field. So that is a plane symmetry. For in such situations, having spherical symmetry, cylindrical symmetry, or plane symmetry, the evaluation of electric field is very easy by making use of Gauss flux theorem. So anyway, these two methods, by Coulomb's law and Gauss flux theorem, we are able to identify the electric field or find electric field due to the cause of the electrostatics, that is a static charge, and we want to find the electric field E. Now in this case, one important equation, that is divergence of E, is of importance. That is, the Gauss flux theorem can be represented in point form as in the form of another equation, that is of the form of del dot E. So we'll get this equation as del dot E is equal to rho by epsilon 0, etc. So I'm not going to the equations, details, etc. right now. Anyway, the divergence of this equation, divergence of E, is of much importance in the case of electrostatic study. So next, another point coming into picture is the conservative nature of electrostatic field. So the first part is the aim behind electrostatics, that is to find the effect due to any cause, that is a static charge, any complicated static charge. And to find the aim, we have Coulomb's law is there or Gauss flux theorem is there. Then another important point is related to the conservative nature of electric field. Just like gravitational field, electrostatic field is conservative. That is, the work done in taking a charge in an electrostatic field over a closed path is equal to 0. That is, if we have a test charge, a source charge somewhere here in the electric field region, and if we consider any point here P and take a test charge capital Q here and move around this and finally reaches at the same point, then the work done for this particular process, that is closed line integral E dot dl, and this will be equal to 0. Line integral E dot dl is equal to 0. That is a conservative nature of electrostatic field. And there is a point form for this equation also, that also is of relevance, that is curl of E, and that means we will find the value of del cross E. In the previous case we find del dot E, and here it is del cross E. And these two equations, del cross E is equal to rho by epsilon 0, and here del cross E is equal to, we'll get it as 0. These two equations are field equations, static field equations. The most important equations of electrostatics are these two static field equations. Now, the next point that we want to discuss in electrostatics is the potential formulation. And the potential formulation actually is a helping tool. Means our aim is to find the electrostatic field, and in order to simplify the aim in certain situations. That means, I have already mentioned, there are different types of sources The sources may be a point charge, distributed point charge, or line charge, etc. Different charges. And also we can see that the electric field at any point E, if you want to find the electric field due to one point charge here, since it is a vector quantity, we can represent it as E1 due to the point charge. And suppose we have another line charge here. This also produces an electric field here. This may be represented as E2. Similarly, we have an volume charge or a distribution of point charges here and there. So all these things will contribute, say E1, E2, E4, etc. Then the total electric field will be E. So we want to find the total electric field as the vector sum of the effects due to different parts of the source or different sources. So this problem is little complicated due to the vector nature of the electric field. So in order to simplify this problem, we are incorporating one term called potential, and it is a scalar quantity P. Potential formulation is to simplify. Now once the potential formulation is done, we are able to find an expression connecting the potential V and the electric field E. And we will have the expression like this: E is equal to minus del V in three-dimensional form. That is, the divergence of V is equal to the electric field. So using this equation, the problem of evaluating the effect due to a complicated source can be simplified. Now, the potential formulation can also be extended to the Gauss-Flux theorem also. So in Gauss-Flux theorem, we have del dot E is equal to rho by epsilon 0, or one equation is there to find the electric field using Gauss-Flux theorem. And in that equation, there is an electric field E. And if we put or replace the electric field E with this expression, that is E is equal to minus del V, then we will get the potential form of Gauss-Flux theorem. And that is of much importance in the case of our cause-effect principle, to find the effect due to a complicated cause. And such equations are called Poisson's equation and Laplace equation. So potential formulation is a helping tool. Then we have one more helping tool, that is the boundary condition. Now, if you are dealing with a problem with the inhomogeneities, that is inhomogeneities in the form of dielectric constant or dielectric contrast, or some charges present here and there, that is a point charge region with a field around it is considered, and suppose there is no other charges present in the form of free charges or in the form of some other dielectric material, then the evaluation of the electric field is quite simple, because we are dealing with a homogeneous region. But instead of this free simple situation, suppose some other charges, charge sheets or charge lines, something are present in that region, or some other bound charges like that present on a dielectric medium, etc. So if there is some dielectric contrast or presence of other charges, the electric field is disturbed. So the calculation in that case are based on such disturbance regions called boundaries. So these boundaries decides what modifications are to be applied to the coming electric field. So these are called boundary conditions. So usually we consider any electric field E. So this electric field may be divided into two situations, that is the tangential component and normal component related to a boundary. If we have a boundary somewhere and an electric field parallel to this is called ET, and an electric field normal to this is taken as EN or DN, and we can see that any electric field may be divided into these two equations, these two forms, and we will find out what happens to the tangential component and what happens to the normal component, and we will find out what happens or how to correct the inhomogeneity situations in the case of an electrostatic problem. So that is problem of boundary condition. Then next point to be analyzed is related to electrostatic energy. We know that the charge is a source of work. If we produce a charge distribution somewhere, allowing different charges to accumulate some point. Initially, suppose we take one charge to a particular location, Q1. There is nothing to disturb that movement because only one charge presents. There is theoretically no work done. Now suppose we are placing another charge near Q1, that is Q2. And for this process, we have to do some work because it is in the field of the first charge Q1 or in the field of the energy distribution of the first charge. And we are bringing the second charge to the energy region of the second one. So likewise, we are able to place different charges and thus we produce a charge distribution. And associated with a charge distribution or even a single charge, we can see that there is some region of field and the region of field can do some work or it is capable of doing work against the charge or by the charge. So this work is in terms or can be represented in terms of the energy associated with that charge or that charge distribution. In electrostatic energy, the density can be represented by the letter half epsilon 0 E square. In the case of free space, we will get this expression as half epsilon 0 E square. In the case of a medium, this changes to half epsilon E square. So this is the energy density, energy stored per unit volume. Okay, so this point is to be considered. Then, before conclusion, I would like to highlight these two equations. That is the most important equations of electrostatics. That is the point equations or differential equations of electrostatics. That is del dot E is equal to rho by epsilon 0. That is nothing but Gauss flux theorem. And del cross E is equal to 0. That is the conservative nature of electrostatic fields. So these two equations are called static field equations. And these static field equations are the basics of electrostatics. So these equations are very much useful in identifying any situations related to any problems related to electrostatics. So we are carrying these two equations to the advanced topics like that. So when we consider magnetostatics in a similar manner, we can see that there are two equations, same form, that is del dot B is equal to 0 and del cross V is equal to mu 0 J. So these two equations we can identify as the static field equations of magnetostatics. And these four equations are called the static field equations. And these four static field equations we will modify in the case of electromagnetic induction case by adding the time variable. So in that respect, our aim behind electrostatics is to study the properties and the associated theories of these two static field equations and the importance of these static field equations in the entire electrostatics and electrodynamics.
So we have discussed the basics of electrostatics, the aim behind electrostatics, and different topics that we are going to discuss in the coming videos. Thank you. Thank you for watching.